Well, hello, Fred. How's it going?
I'm doing okay.
All right. Great. Well, it's Chem 106. How'd you do in Chem 105?
I'm here, alright.
Well, what does that mean?
I passed. I'm okay.
All right. Good. Excellent. Are you excited about Chem 106?
Uh, actually, I learned a lot. I can't say I'm really excited, but I definitely can tell that I'm learning.
Well, that's good. Good. That's important, right?
Yeah, I guess so.
Well, I mean, the stuff you're learning is real stuff, right? I mean, it might be man's interpretation and man's models around the stuff, but these are eternal principles, right? Definitely natural law stuff, right? I mean, stuff of this of that governs the laws that govern this world.
Okay, yeah, I get that. So, what is it, chapter 11?
Oh yeah, chapter 11, properties of gases. All right. Now we're going to talk about gases, liquids, and solids moving forward a little bit, and solutions eventually. And the reason why we're kind of in this position to talk about gases is because our previous chapter taught us how to make Lewis dot structures. Do you remember that?
Yeah, I remember Lewis dot structures.
So Lewis dot structures, after we get the Lewis dot structure, we can determine whether or not a molecule is polar or not. Do you remember the polarity thing?
Yeah, I remember that.
So, for example, carbon dioxide, do you remember if it's polar or not?
Carbon dioxide?
Yeah.
I'm not sure.
So, what we do, remember, is we draw the Lewis dot structure, and hopefully you remember that well, I mean, I'm just going to skip right ahead to the Lewis dot structure. You'll have to go back to chapter 10 and 9 if you want to kind of review how to do the Lewis dot structure. But looking at that compound, would you say it's polar?
Well, it's probably carbon and oxygen bonds are polar. So let me think.
Is there anything else that it has to be taken into account when you're determining whether it's polar or not?
Oh yeah, the what do you call that?
Symmetry?
The symmetry. Yeah, the symmetry.
Yeah, the symmetry. So what shape is this compound that I have drawn here?
The central atom has two regions of electron density around it, so that's linear.
That's right. It's a linear compound there. And even though you're right, the carbon-oxygen bonds are polar, the resulting molecule is nonpolar because it is symmetric. All right? And that can be compared to something like ammonia, NH3, right? NH3 here ends up having one region of lone pair electron density, four regions, so that's tetrahedral, but the one region of lone pair density makes the compound asymmetric, and that asymmetry results in polarity. All right? So asymmetry isn't generally all you need. We also have nitrogen, which is a fairly polar atom, or electronegative atom, strongly electronegative atom. Do you remember how to determine electronegativity?
Oh yeah, I think so. It's just like the periodic table, right?
That's right. So we have the periodic table here. Let me bring this in. And remember, nitrogen, oxygen, and fluorine are our three most electronegative atoms, with fluorine being the most. Nitrogen is actually above everything except for oxygen and fluorine. So yeah, we got some pretty electronegative, or nitrogen is a pretty electronegative element, and those nitrogen-hydrogen bonds have electron density moving towards that nitrogen. So this is polar. And what that results in, now both of these are gaseous. This is carbon dioxide and this is ammonia. All right, let me write their chemical formulas up here. Carbon dioxide, ammonia. But what this polarity does is it creates, remember how we can kind of label the polarity? How we can kind of write it on here?
No, I don't remember that.
It's like with these delta.
Oh yeah, I remember this.
Delta negative, right? And we can write delta positive signs over here because there's a slight, that's what that delta means, negative charge on this side because of the electronegativity of nitrogen, and slight positive charges on the other sides of those polar bonds. Okay? And what that does is it makes a neighboring molecule of, can you hold that for me for a second?
I got you.
All right, thank you. So a neighboring molecule of ammonia, one that's nearby, will have a degree of stickiness because the partial negative is here, partial positives are here. So two molecules of ammonia will stick to each other to a certain degree between these partial positive and these partial negative charges. All right. Carbon dioxide, on the other hand, does not have those partial negative and partial positive charges, and so there's really very little stickiness between the compounds. And that's that stickiness which results in whether a compound is a gas, liquid, or solid. The stickier they are, the more likely to be either a liquid or a solid at room temperature. These are both gaseous, we said that before, but this increased stickiness makes the what we call the boiling point of this compound, the ability to separate those two, is higher than that of carbon dioxide. All right, so we're in a position now to talk about gases because our ability to look at Lewis dot structures and identify the compounds, the resulting compounds' polarity. Now there's some important equations that we'll introduce here in this section about gases, but that's why we're moving on to gases at this point. All right. Gases are compounds that, in their container, because the molecules don't stick together, they will take the shape of whatever container they're in. All right? So if I had a container that looked like that, just some odd container shape, right? And I had a spigot here and I pumped it full of gas, the gas molecules would fill and go in every space there, right? I mean, you can imagine if I put some solid in here, it would just kind of clump up down here at the bottom. It would just fall down and clump at the bottom. But whatever the shape the resulting the container is, gas will take every corner of it, right? When we fill up a balloon, which is saggy, right? The balloon takes a shape, and that balloon now is filled every corner with that gas, and that gas is the same concentration in every corner. The molecules are all spread out from each other. They move around. Here they are. I can draw them like this. I can draw them with little vectors kind of moving around. And when they collide, they bounce right back. They bounce away from each other. They're not sticky enough to each other to do anything other than bounce away from each other. And so it can have an indefinite shape. The volume of a gas, and this is kind of giving away some of the punchline of this chapter, but because the molecules are not sticky, they just kind of move around, the volume of gas is related to the amount of gas you have, or what we like to use in terms of amount in chemistry is moles. So every mole of gas that you have, if it has the ability to spread out as much as it can, it will take up the volume of 22.4 liters. 22.4 liters. So at STP, which we call standard temperature and pressure, one mole of gas will always take up 22.4 liters. Now that doesn't matter if it's a mole of carbon dioxide or a mole of ammonia or a mole of octane. Whatever the gas is, at standard temperature and pressure, it'll have the same volume. And that's because regardless of how large the gas molecules are, or how small they are, so you talk about something like helium gas, really, really tiny, right? They behave like little balls bouncing around. And so the size that they take up has to do with how fast they're moving, their motion, and that's related to temperature. We've already talked about temperature being related to how fast they move. It's related to the surrounding pressure. So if we're up in the mountains, right, where there's less air pressure from the air that's outside of the balloon, then a balloon would expand. If we go down to the bottom of the ocean, the balloon would contract, right, because the water molecules are pushing on the outside of the balloon, okay? So it's related to the number of moles that you have in the balloon. It's related to the air, the pressure on the outside, and it's related to the temperature. Okay? Now, when you think about bubbles rising in liquids, right, like carbon dioxide gas that's dissolved in soda pop, you open the soda pop, pour it into a nice clear cup, and you see the bubbles rising to the top. Those bubbles are rising to the top because the gas that's in those bubbles is much less dense than the water that's in those bubbles.
Yeah, I can see that.
Oh, that makes sense?
Yeah, I understand density, I think.
All right, good. Now, the density of different gases is not the same, right? So if I have two bubbles, one bubble that contains helium gas and one bubble that contains nitrogen gas, their densities will be different, right? A balloon, so here's a little review. What is the atmosphere made up? What gases are in the atmosphere?
It's oxygen, but I remember you said that it's mostly nitrogen.
That's right, mostly nitrogen. So when I blow up a balloon, I'm blowing it up with mostly nitrogen, about 19, 20% oxygen in there. But when I blow up a balloon, it won't just float away. It has the same density in it as the air around it, and so it will stay, basically, it will not float away. The mass of the balloon itself will be heavy, and so that's why they fall to the ground. But if I fill a balloon with helium, that same volume, right, relates to a significantly less mass because helium, pull up our periodic table here and remind ourselves, helium has a mass of 4. Nitrogen gas would have a mass of what?
14?
Well, it's nitrogen gas.
Oh, yeah, 28.
That's right, N2, 28. So 7 times more dense than helium, right? All right, so there's a little preview, a little discussion about gases. And there's a lot of cool stuff that we're going to learn moving forward. All right, see you in video 2.
Okay.